Okay. So I want to do a couple things today. There's some issues with the analyzing this off-axis hologram using Fourier analysis. So we're going to do that. So we kind of got to start on that last time. After that, then I'll look at some different types of hologram geometries that have proven quite useful for various applications. And then after that, if we have time, I'll start on the image analysis of holograms. And this one I actually have word processed. I haven't put it up yet, but it'll be a lot more legible than probably my chicken scratch handwriting. I'll try to do better, but I usually fail. All right, so let's start on that.
I'm sorry, what was WQ for?
Oh, word process. Yeah, okay. So just a little excited about that. Yeah, and then just for your notes here too. So we'll have lab 2, not next week, but the following week, which I guess is like the 5th and 6th of October. And the midterm is going to be on the 22nd of October, I think. Is that? Yeah, that's the Thursday, by popular request. And so there'll be more coming out on that shortly. All right, so let's start looking at the off-axis hologram analysis using our Fourier tools that we now have. So again, we're going to place a kind of an object transparency here, all right? And let's see, when is homework 2 due? Tuesday? Okay, yeah. So I'll have another homework assignment. There'll be a problem sort of along the lines of this analysis a little. So you'll be asked to evaluate a few things in that. And maybe Tuesday I'll clarify a couple of things there for you, because I always get the same questions. But one issue that always comes up is the spatial frequency. So the spatial frequencies for, if this is our object transparency here, one simple way to do this is to just assume that we have basically like a localized grading there. And so if we have a normalized, normally incident plane wave, we can use our grading equation like so, and say one of these is 0 if we're normally incident. And so we just have the sign of this diffraction angle now that we're going to get, say, coming off this. And we could have, a Q here, and Q could be a plus and minus order. It could be multiple orders as well. But at any rate, that's what I mean, if I give you a object transparency and give you some, say, feature size, like 1,000 lines per millimeter, which is like 1 line per micron. So then you can insert that into the grading equation and come up with an angle here for that sort of object projection or object wave that's coming off of that object transparency. All right, and so again, so this was located at Z0 away from the film plane, and then we come in with a off-axis plane wave here. And again, for some strange reason, we use 2 theta rather than theta, but we'll just go ahead and use that. And then again, all these waves kind of interfere here. And so we have now a situation where the field, so we have this field coming from the object, and then we have this, this reference beam coming in, this off-axis reference beam. So we have at the film plane, we then have that u, if we have coordinates x, y, is equal to the reference beam. Let's just give it a unit amplitude. So this is just exponential of minus j 2 pi times alpha x, and plus the object wave a, we'll call this wave here a of xy. And this alpha is just sort of the spatial frequency along that x direction for that wave, and that's just equal to the sine component of the propagation vector, sine of 2 theta over lambda. And we can say that, k sub x, say for instance, is equal to the x component of that propagation vector. If we were to say that's k, is just equal to 2 pi sine of 2 theta over lambda, or 2 pi times alpha, okay? Just to relate it back to a few other things. All right, so, and then this a of xy will give it a amplitude, maybe not unity, and varying along the position here in the film plane with a phase e to the minus j phi of x, y. All right? And then, of course, so we're going to get this interference occurring if these are two coherent waves. So we have a plus r, as usual, squared. And this, then, if we write this out in terms of, we could write it out in terms of exponentials, or we can combine it. And so let's just go ahead and combine it this time. So we have, or maybe more precisely, we write that as a square for the a term, and then we have plus a, well, let's see, I'm sorry, I was saying that's unity, but let's just give it a an amplitude of a for the reference wave, since that's what I have in my notes. A times a tilde of xy, and then we have a 2 out there, all right? And this then is times a cosine of 2 pi alpha x minus phi of xy, all right? And so this now gives us, the idea that we have here, we have this carrier wave or reference kind of interfering with the object wave or object phase here. And so you can see that if we wanted to separate these two, we may have to have a special relationship between that carrier wave phase and the object wave phase in order to separate. And that's exactly what we're going to look at today. All right? So again, so this is our intensity, and then of course we can make a say an object or film transparency, hologram transparency, T sub f of xy, by multiplying or by processing the film. And so that's going to give us something that looks like a kind of a bias term plus, if this is the film response, the after development, we have a gamma that we talked about in that Herter-Driftel curve for the slope, basically, right, times the intensity function that we have here, I. Okay. And so this this is basically the hologram. Okay, and so here we could say then that we have 4 terms. So we'll just break this into 4 terms, and we're going. This will be a little bit helpful in breaking it down in that way. So we have the first transmittance term is just this base transmittance or bias transmittance that we might have. The T2 is going to be equal to, we call that, say, beta prime, that product. This is like the exposure time, and that's the gamma, the linearity of the film response. So we then have beta prime times A of xy for the second term, quantity squared, and then we have T3, the third transmittance component is, again, beta prime A times A for the object amplitude times e to the j 2 pi alpha x. All right. So in last time I kind of gave the prior step here, but you can look back and see that. We can, of course, we have a cosine, so we have the phase of the object and we have the phase of the reference field here, and or the phase of the reference field is there. And so this gives us this term, and then we have a T4, which is beta A tilde object field star of xy, and this is times e to the minus j 2 pi alpha x. All right. So yeah.
Why do we call it beta prime instead of just beta?
That one.
Well, in general.
I don't know. I was just trying not to, because later. Okay, so. Okay, in the next step, I was going to illuminate it with a field that I was calling B. So I thought it would be a little less ambiguous.
Do you know if there was some special reason we were avoiding the use of beta? Or?
Yeah, I think what I'll do is I'll just call that R instead of B, and then I could use, beta. All right. Any other questions so far? Okay. All right. So kind of straightforward. We're basically doing our hologram recording, and now the analysis. All right. So now we're going to reconstruct this. Okay, and we're going to reconstruct it in a different way. Okay, so I drew this out a little more neatly here so you can see what's going on. So here we are, instead of in the construction, right, we had the reference beam coming in at an angle, all right? But for the reconstruction now, we'll do this a little differently. So we're going to come in with a normally incident plane wave into the hologram rather than an off-axis plane wave. And what that's going to do is it's going to shift the images off-axis, basically, off of this. If we reconstructed it this way, we would reconstruct the image here, and then we'd have a virtual image in the back, right? But this way, we can kind of move those off the axis to separate them visually. So here, when we do that, we have the original object wave is going to be in this direction out here. And so if you were looking at that field coming out, those rays would converge to a virtual image located that distance z0 away from the film plane. All right. And similarly, reconstructing it again with this wave here, we're going to get another wave out here, which is going to converge to what looks like a real image. All right. Now, in actuality, this one will probably be not a very good image, but we will get some light converging there. Okay. But for now, we can say that, okay, we'll get a real image and a virtual image when we reconstruct this. Because notice, well, it's not showing up here, but all right, well, I'll show it shortly. But anyhow, if we were just to illuminate this with a plane wave we would get one of these reconstructed, with good fidelity, the other one with not such good fidelity, basically, because of the fact that we're not, we'll have R times R versus R times R star for one of these, depending upon whether we use the original object field or a conjugate object or reference field illuminating that. Okay. Okay, so we're going to use this particular reconstruction geometry, and so now these four transmittance terms are going to give us, and again, I'll use R for the reference field amplitude. The other nice thing about that is we don't have to throw in another phase function into it, which we could pull it out again, but this way, the e to the minus j k dot r, this just goes to 1 along the z-axis, and so we're in pretty good shape with that. And we could just represent it as an amplitude here. All right. So we have now the reconstructed field components. We have u1 is equal to this t sub b times r. We have u2 is equal to r times, since I use beta prime up here, I'll use it here, for this product of gamma times tau times a of xy squared. And then we have u3 is equal to r times beta prime times a tilde of xy times e to the j 2 pi alpha x, and u4 is equal to r beta prime a star. This is just a constant, not a complex number, so we don't have to conjugate that. Here we would have conjugated it, or would have been conjugated. And then we have e to the minus j of 2 pi alpha x, all right? Okay, so we have these several different terms here. And again, so in here you can explicitly see that, if we control A in a certain way, we're going to get exactly the object field coming out of this, or the conjugate field coming out of it, okay? And in actuality here, so let me maybe retract what I said a little bit earlier, because the other advantage of this, which I just now noticed here, is that if you re-illuminate this with this reference wave that you can just represent as a constant, right, then you actually do get A and A star, unambiguous, because these are just constants, okay? So you just have, this has no phase. The only phase you have is the phase that was recorded during, the recording step, which is this e to the j 2 pi alpha x and e to the minus j 2 pi alpha x. So you actually do get, in this image, you actually do get both the virtual image and the real image looking pretty much like what they're supposed to look like, okay? You see that? Before we had a problem because this r had some arbitrary, it was a tilde, right? And so we had some arbitrary phase in there, which didn't cancel unless we did either r or r star. But now we just have a constant, and so things work out much better, okay, in that sense. Okay. All right. So we have these field terms. All right. So now let's do a little bit of play with our Fourier tools here. So let's do the following. Let's take the Fourier transform of the field terms. And then what we'll do is analyze the frequency characteristics. Okay? All right, so if we take Fourier transform of the first term, we get a G, we'll call that big G here, And we have some frequency variables, f sub x and f sub y, which is like x over lambda z and y over lambda z, as we mentioned before. And this is defined as the Fourier transform of T1 of xy. And so what do we have here? We have basically a constant, right? So that's pretty easy. So then we have simply TB, which was this amplitude, and if we let r equal 1, okay, we're just going to have TB times a delta function, oops, f sub x, centered in our spectrum space that we have, okay, on the axis. All right, so that's G1, or the first term. The second term, so we get to use our Fourier relationships because we have this field times its complex conjugate in that term. Again, so this is Fourier transform of T2 of xy. And so this is equal to, I don't know, I'm carrying this beta around, so we'll carry beta prime around. Beta prime, and so we have this, we take the Fourier transform of that, and so that, as you recall, or may recall, is the autocorrelation function of the Fourier transform of A, so we'll designate that as G sub A, f sub x, f sub y, and again, it's the autocorrelation function with itself here, G sub A, fx, fy, okay? Again, back from our Fourier definitions that we had during the first part of this. And again, so this G sub A of fx, fy is equal to the Fourier transform of A of xy. Okay. All right. Now G3, the third component here, G3 of fx, fy, this is equal to, again, Fourier transform of T3 and that's equal to beta prime A, I don't know why we're carrying A around, but anyhow, we will, G of A, right? So we have the Fourier transform of that. But we also have this phase term in there. And so if you remember our relations, that's going to give us a shift, right? So we have f sub x minus alpha is what we're shifting it by in the x direction, f sub y, okay? And similarly, G4 of fx, fy, this is, again, the Fourier transform for completeness here of T4 of xy, beta prime A, and this is GA star, since we're taking the Fourier transform of not A, but A star. And here we have minus fx minus alpha fy. All right. Okay, so again, we get the shifted spectra in the result. All right, so now let's say, so we had this object field, right, that we took the Fourier transforms of, or this object spectrum value, or A, right, we took the Fourier spectrum of that. So let's say that this, when we do this transform, that this is going to be band limited, meaning that it doesn't have an infinite frequency response. It has a finite frequency response. So, finite frequency range. All right, and so we can represent that. So this object spectrum, we can represent that in the following manner. So we have here, say, an fx and a Fy, and this is the magnitude here, or the value G sub A. And so this is going to have some kind of interesting functional form here. But the main part, or the main point here, is that it's going to be limited in frequency range, is the point I'm trying to make here. So this is our B sub f, and we have a minus B sub f there. So the total frequency range for this object function is 2 B sub f, right? So we have a B sub f there. All right. So that's what I mean by a band limited function, or a finite frequency range for that function, because that's going to be important now in looking at what we have. All right. So let's look at all of these frequency components are part of the reconstructed field, right? There's not just one of those, but there are all of them. So let's go ahead and plot those. All right. So if we plot our f sub x and f sub y, like so, the first component is a weighted delta function, right? And so we end up with a delta function located on axis in the middle of that frequency spectrum, and has an amplitude of t sub b. Whatever the transmittance value is for that hologram, that's the magnitude of that spike right there at the center of our spectrum. Okay. The second term is an autocorrelation function, right? So it's a convolution of the function with itself, right? And so whenever we have a convolution of two functions, we end up with a total frequency range that's equal to the sum of those two, right? So we end up with another component here in the middle, which has, again, so this has one of these Hershey Kisses type functional forms, is what it kind of looks like, to me at least. So here we have a value of 2 beta f, and also another value out here, 2 beta f. All right, so we see that that's the range of this autocorrelation function. So this is G2, this was G1, and now the other parts, G3 and G4, those are kind of the more interesting ones. So again, so we're going to be, so if we look at this, G3 is shifted, the center of that frequency spectrum of that component is shifted by alpha, right? Yeah.
So is TB of G1, is that just a spike in the middle, and then G2 is?
Yeah. This is a delta function.
Okay.
Right?
I wanted to make sure I understood.
So there we have that delta function, but G2 is this autocorrelation function, so we get, again, that convolution of the function with itself, so we end up doubling the bandwidth that we need to represent that autocorrelation. All right? So now, so G3 is out here, located a distance away of alpha, all right, and we have its G3 is centered right there. So we have a smaller Hershey Kiss candy out here. And it also has this 2BF for the half bandwidth. And there's another 2BF in here, like so. All right, so this is G3, and G4 is out on the other side, right? We have the negative Fx, and so this is shifted out here, minus alpha, and there we have another function looking like that. So this is G4, also with 2BF as the range there, okay? Oh, I'm sorry, not 2BF, this is BF. This is the only one with 2BF here, is that autocorrelation. I'm sorry. Yeah, anyway, so that's that. It's just that shifted function. So now, if you look at this, you can immediately see what requirement you need on alpha in order not to have ambiguity in the reconstruction, right? It's 3BF, right? Because alpha, so what we need here, so we need alpha must be greater than or equal to 3BF in order to get us away from this autocorrelation and not have overlap with this other shifted element located this alpha away. All right. So, and that has a width of BF. Okay. So, in order for us to not have ambiguity for unambiguous reconstruction, this has to be the case, all right? However, having said that, all right, so anyway, so what does that imply? What is alpha? Alpha is, again, sine of 2 theta over lambda. And so we see that this 2 theta, the minimum angle that we need, which is 2 theta, must be greater than or equal to the inverse sine of 3BF times lambda. And again, BF could be like 1,000 lines per millimeter or 500 lines per millimeter, something like that. Okay? Now, having said that, notice that we will have, we could have, when we do this reconstruction, the zero order, or this autocorrelation function, may not be very strong. Okay, so if we have a kind of a less restrictive reconstruction, meaning that this a squared that we have here is, say, much less than r times a that we're using for this G3 and G4 component, then we can say that we have, all we need here is just that alpha is going to be greater than or equal to BF. Okay, because we don't have to worry about this. So we can put this, alpha can be, it just has to shift it enough so that this is on one side and this one is on the other side of the axis. Okay, so let me draw that out, make that more clear. So now, so here we have alpha, and then we're going to have this shifted over on the other side. Made it a little too long. Here's minus alpha. That's supposed to be BF, BF, and that's also supposed to be BF.
So that's the G3 and G4?
Yeah, so this is G3 and G4. So now we have alpha just has to be greater than or equal to BF, okay? Because as you can see here, that's going to change, the angle that we need in one case is going to be much greater in this more restrictive case than in the other. So let's just throw some numbers in there to see that, all right? So we have a little example. All right, so let's say that we have a wavelength of 0.5 micron. It's always a safe bet. And we have the the bandwidth of the function that we have is 1,000 lines per millimeter, which is also a 1 line per per micron. Okay, so we have minimum feature of, say, 1 micron in that transparency for the object function. So if we have this, less restrictive condition again, so now we can say that the sine of 2 theta over lambda is just equal to BF, right? So we just take the equal sign there, which is equal to basically 1 over the period again. And so we have now that 2 theta for the reference beam angle must be greater than or equal to 30 degrees. Okay, so that's not too hard to realize in the lab. So if we had now the more restrictive case, yeah, a more restrictive reconstruction condition, I guess. All right, so in that case, we'll have alpha now is equal again to sine of 2 theta over lambda, and this is equal to 3 times b sub f. But now, if you look at that, we have 3bf. This is equal to, well, let's see. If we take sine of 2 theta, that's going to be equal to 1.5. Okay, so there's no real angles that are going to do that for you, right? The maximum value you can have is 1. All right. So we're stuck there. So you can see that if we have to work with an object with that spatial frequency, we can't really do it. All right. So what's the maximum spatial frequency we can get with this wavelength? Well, okay, so that's just going to be equal to having this b sub f equal to 1,000 lines per millimeter over 1.5. Okay, so which is 3 times half a micron, right? 3 times half a micron, or 3 times this, half a micron. And so that means that our spatial frequency is going to be like 667 lines per millimeter, but that assumes that the angle that we have, this 2 theta, is equal to 90 degrees, which is kind of hard to do. Okay, so let's say we can only do 60 degrees. So if we have 2 theta equal to 60 degrees, then the max b sub f that we can record, it's about 557, somewhere in that range. So it falls off pretty gently there. So again, so that just, doing this frequency analysis, you can get a kind of a totally different perspective on this. So in the homework problem, if I recall, what I asked you to do is to look at this now a little bit more from, I think I asked you to look at the range of angle, or how close you can separate the film. I guess it's this object here, or this figure. How close you can position this. So what you have to do there is play with the geometry a little bit. So it's more like an experimental setup. So I mean, you can't bring this transparency in such that you're clipping this field here, right? So it's, I don't know, the question, I should have maybe reconditioned it a little bit, but nonetheless, I was just asking you to look at more the geometry of this, and I'll go over that again on Tuesday. Well, it's going to be on homework 3, okay, which I haven't given yet. So you are going to have a question on this work that I'm covering here. So, and I think I then asked you some questions along with the Fourier analysis of that configuration. So, okay. All right. So now let's move on to the next topic. Any questions on this that we have here? So, again, I think it's kind of interesting just to show you a different way of looking at the recording process from a frequency perspective, okay? All right, so let's do something else now. So let's look at some hologram geometries. And we already have done two, right? We've done the inline hologram where we have, so we have this geometry where we illuminate our transparency here, and then we have the film out there. We get, again, that scattering, and we have residual reference beam, which propagate to the film plane. And then during the reconstruction, when we do that, you end up with one reconstruction here. You get the residual reference beam, and you also get a, which is, this one is a kind of a real image, and then there's a virtual image also, which is formed out here. And all of those, again, occur at the same time. and so there's overlap of all three images. So we have the real, we have the virtual, and we also have the reference beam. Okay, and then we also have this this off-axis hologram. And so here, what we would do, again, so we can actually illuminate this now without just having a transparency, but we can actually have a three-dimensional object. We illuminate it. Here's our film plane, like such, and then we have our off-axis reference field here at some angle, theta. And so we'll get an object wave recorded with that reference wave, and then we can for the reconstruction of that, if we just use the reference field, same original reference field, we would get the object field giving us this virtual object like so, and there may actually be a kind of a messed up real image out here. I'll put that in parentheses because it's not, in this case, because we don't have this nice plane wave that we used in that prior example, we're going to have something that kind of has the object wave in it, or the conjugate of the object wave in it, but we're going to also have the product of the phases for the reference field times the reference field, which is not going to cancel, and so we're going to have some biasing phase going on there. Okay, so we already have these two geometries, but there are some other geometries which are also very useful. So let's look at those, all right? And one, all right, so now we can again use some of this this nice Fourier analysis that we have, and we'll look at the Fourier transform hologram. All right, so here is our, so we're going to have an object out here on plane x1, y1. So again, we'll use, this time we'll have a object transparency here, which has some function little o of xy, and then, so here, and here's the axis of our system, like so. All right, and then in order to form the reference beam, we could come in with a plane wave off at an angle, Or we can do something else, all right? So we'll bring this out just to illustrate another clever way of doing this. So what we can do here is put a lens with a short focal length here, and we can illuminate this whole business with just again, a normally incident plane wave, all right? So this part of the plane wave hits this lens and brings it to focus in this spot here, which is located, say, a distance b below the z-axis, all right? So what you now have here is a expanding wave that comes out of that hole, basically. It's like, our spatial filter that we had in the lab setup, all right? And this field here also, we're going to get some expansion out here from from the object transparency. So we have those waves coming out. And so what we want to do now is to make a recording of the Fourier spectrum of that object wave. So what should we do here in this? Remember? Okay. Well, we could let it go a real long distance and we'd be in the far field, right? And so we'd have kind of a Fourier spectrum of this object field if we did that. Or we could put a lens here, right? And we could put the lens there and put the object transparency exactly at the front focal plane, right? We derived that last time. And then if we go here in the back focal plane, another distance f in back, here is where we're going to put the film. All right, and so what we'll end up with then is so we're going to have this plane wave coming off here at an angle theta, all right, and the tangent of that theta for the reference wave, theta r, is going to be equal to b over f, right? It's this distance over that length, all right? So that is, we have this off-axis plane wave coming in, and it's off at a little bit of an angle to the z-axis, all right? And here we're going to have the spectrum of that object transparency. So here's the object spectrum, and we'll give this a kind of a script O and we have coordinates x2, y2. Here's coordinates x1, y1 on the object plane, like so. All right. All right. So now if this is a small distance b, this is about equal as well to the sine of theta r. Okay. And so then we could, so this is good because now we can say that, we have this alpha again, which is equal to sine of theta r over the wavelength. All right. Okay, so we have our reference wave r. This is just equal to an off-axis plane wave that's hitting the film. So we have e to the j 2 pi alpha x2, and we have the object wave, which is the spectrum, right? So we have O of x2, y2, and that's, again, equal to the Fourier transform of little o of x1, y1, all right? Okay, so now these are our two fields. So again, we want our intensity for the recording. That's equal to r plus o squared. That's script O. And so again, if this has an amplitude of 1, so we have 1 plus O of x2 y2 squared, and then we have plus O of x2 y2 e to the minus j 2 pi, the conjugate, which is e to the minus j 2 pi alpha x2, and then we have plus O star of x2 y2 e to the plus j 2 pi alpha x2. So this is the intensity recorded at the film plane over here. Okay, so we go ahead and do that recording, and now we want to do a reconstruction. All right. Keep my pages numbered here. So now for the reconstruction, of course we're going to turn that into a transmittance function, and that like we have in the past. Basically, it's going to just reflect that intensity in the transmittance function. And so in the reconstruction, where we have a field W, which is going to be generated, which is just equal to, say we reconstruct it with the original reference field here. So we're going to have R, and then we have, oh, I forgot to, sorry. So we're going to reconstruct this, and we'll do it in such a way that we have a, again, we're going to use our lens to create this inverse Fourier transform in the system. I'm sorry. Yeah, so we're going to have a lens in this. So we're going to have our film plane here. This is now the hologram that we have. And to do the inverse transform, we'll use another 2F system, right? So again, as I mentioned last time, we have we'll use these 4F systems a lot. So we have 2F system in the recording phase and a 2F system in the reconstruction phase. All right, so here again, here we have F out here, and we're going to look at what happens in the back focal plane. All right, so during the reconstruction, all right, we're going to illuminate this now with a normally incident plane wave out here, and so our field now just past the hologram is going to have R times 1. It's just basically this out here. So we have 1 plus the O, this spectrum of x2, y2 squared plus O of x2, y2 e to the minus j 2 pi alpha x2, and then plus O star x2, y2 e to the plus j 2 pi alpha x2. All right, so that's what we have right here. This is, say, where this field W is. And now what we do is, again, so what we're going to do here is we're going to take, again, the Fourier transform of this function of W. That's what's out here. And so we're going to get the Fourier transform of W out in this plane. So what does that look like? All right, well, the field in this back focal plane, we'll call that U sub f here of, and we'll give this coordinates x, y. U sub f of x, y, again, Fourier transform of W, that's going to be equal to, again, this reconstruction field that we have, R, times the Fourier transform of each of these components. So first component is a delta function located right on the axis. The second term is the autocorrelation of the object wavelet itself, right? So here we have O of xy, and we have the autocorrelation with itself. Okay, and then we have out here, we have again this with the phase term. All right, so we have O of a shifted axis for that term, x minus b, y, and then we have O star of minus x plus b minus y. So that looks a lot like the previous case, right? And so if we actually then look at what we end up with, we'll find, let me draw it out here first and then we'll look at some pictures. So we're going to end up, we have that delta function again. So we have the delta function, and then we have this autocorrelation term, so we're going to have some stuff out there, and then we're going to have something shifted here by b, and something downshifted by minus b, just like that. So it looks, it's identical to what we just derived for that Fourier analysis. And some of the images, I took these out of an old book that I had from Hariharan, who was an Australian, as you might guess. So here is that autocorrelation function here in the center. And there's a delta function in there, although it's sort of blotted out. Here you can see maybe that, delta function a little bit better. And these are, again, the two images that we end up. And notice that they're inverted, okay? So this inversion relates back to the fact that one is the original object, but the other is the conjugate, okay? And so you get this kind of inverted image for one and the true image or the original image for the other one, okay? All right, so that's one additional geometry that we might have. We can do some other things as well. So there's another geometry which is very similar to this, and this one is called the lensless Fourier transform. Put that in parentheses. Geometry. Now, it's not completely lensless. That's why I put it in parentheses. In the construction phase, you don't need a lens, all right? And so here, in the construction phase, we have, again, here's our, say, our optical axis, and we have the same kind of situation that we had before. So here is O, this object transparency, O of x1, y1. And then we have out here, we're going to put, again, a little lens and a hole in that screen, focus the light down, and kind of let it project out there. And we then have, kind of the diffracted field coming out here as well. And so, again, all this is normally illuminated with a plane wave, like that. All right, so now we place our film out here again. And this is located at a distance z0 away. All right, so, and again, that's B below the axis. All right. All right, so the object field then that after propagating this distance, which we'll say satisfies the Fresnel propagation requirements, okay? So the object field that we're going to have then is O of x2, y2. The film coordinates are sub 2's. So you have O of x2, y2. And this, according to our Fresnel propagation relation, was or is equal to 1 over j lambda z0 times this phase term, exponential of j pi over lambda z0 x2 squared plus y2 squared. And then we have the Fourier transform of, as usual, the object field times the quadratic phase factor. So we have O x1, y1 e to the j pi over lambda z0 x1 squared plus y1 squared. Okay, and close like that. So that's the object field coming out here, and then we have the reference field. So the reference field is a expanding spherical wave, right? That's what we have here. And it turns out that it's a very, it's kind of a special spherical wave because the r of x2, y2 that we end up with now is equal to, if the distance is reasonably far, we have perhaps an amplitude r over z0 exponential of minus j pi over lambda z0 x2 squared plus y2 squared. And then since it's shifted, exponential of down here, we have exponential of j 2 pi x2 over lambda z times b. And so this, we can say that that's equal to, say, a different variable, kind of a normalized variable, spatial frequency variable. So notice that what we're going to do, right, as we normally do in making the hologram, we take the intensity of those two. And so we're going to have products of R and O and O and R star, right? And so the intensity that we have, I, and notice here we have this quadratic phase factor out in front from our normal Fresnel propagation, but our choice of reference field, which is a spherical reference field, in the quadratic approximation again, has that same phase factor and only with the opposite sign to it. So they cancel when we take these products. So we don't, So we don't need the lens there in order to get rid of that extra phase function for this case. So we have for our intensity, again, R plus O squared is equal to 1, and we'll use these these spatial frequency coordinates here, O, chi, and eta, where eta is y2 over lambda z. This quantity squared, and then we have a factor out front here, 1 over j lambda z0 squared, O, the Fourier transform of chi, eta, and then we have that shift term, e to the minus j, 2 pi chi b, and then we have plus 1 over j lambda z0 squared, O star of chi eta e to the plus j 2 pi chi b. All right? Okay, so now when we reconstruct this, so now we cheat, okay, in a sense. So now we're going to take this, so cheating in the sense that it's no longer lensless, all right? So here's the hologram here now, and so now we need a lens here because we don't have anything else to get rid of that quadratic phase, and then we use it in the front focal plane of the lens. We illuminate this, and in the back focal plane, again, we end up reconstructing a set of terms. So u in the back focal plane, xy, we end up now with the Fourier transform of all these terms here. These are just constants, so we'll kind of knock those out. And so we have a delta function from this, just like we had before. We have the O of xy autocorrelated with itself. And then we have plus O of x minus b y, and then we have plus O star of, say, x plus b y. All right, so the reconstruction looks pretty much the same like it did for the total, the complete Fourier transform hologram. All right, not too surprising. We just took advantage of the fact that we were able to get this phase cancellation out here by going with a point reference field, this point expanding reference field. Now, this particular geometry is quite useful in holographic data storage applications. Okay, so and the reason for that is, notice, so in those applications, they use a 4F system in that, so 2F going in, 2F coming out in the reconstruction. But the object field now, instead of like recording the whole hologram with the object field, you can condense that into a small region where you have just the Fourier or the frequency spectrum for that object field. And so that constricts the region where you need to utilize in order to do the recording of all of those frequency components. And so this is a very sort of space-efficient way of doing a recording for data storage, because you want to store the most data in the least amount of space. Now, I see some of you a little bit skeptical in a sense. Some of these frequency components are going to be, extend pretty far out. However, usually the amplitude of those are very weak, so they don't contribute very much to the reconstructed image. In addition, the images that are being recorded are usually kind of bit patterns, right? That would be set up by a spatial light modulator. If you remember back to like the first lesson or two, where I talked a little bit about data store. I'll talk more about it in a separate lecture later. But normally you have a bit map which is dynamically upgraded by doing it not in a transparency like you would have here, but doing it in a spatial light modulator that you can reconfigure electronically. And so then you can record one spectrum, and then you can record another. You can actually record several different spectra depending on the dynamic range of your material in the same spot, and then you can shift the material around. The best kind of holographic data storage systems are kind of write once and read many kinds of systems using photopolymer, and they use something similar to like you have for a CD player, where you do the recording on a disk. And the reason they did this was because all of the mechanics and the readout capability have already been developed for CDs and DVDs and so forth. So all of that technology was already developed. So I was actually involved on a project where we morphed from going to recording lots of data in a very traditional way in a very thick crystal, photorefractive crystal, to going to a disk recording system. And the main reason for doing that was practicality. There was no good way to store the amount of data that we needed in a block slab of material. We would have had to develop a whole new mechanism for stepping and repeating and so forth. Whereas, the rotating disk technology is very well developed. So again, it's kind of an interesting transformation there. But anyway, they do have these data storage recordings which utilize this Fourier transform recording setup. Okay. So we have just 2 minutes, and that will be enough time to talk about one other kind of interesting hologram form, and that is what's called an image hologram. All right, so the image hologram, and when we do the image analysis, we'll kind of verify some of this stuff. But in an image hologram, here's your object out here, and you illuminate it with an illumination beam, and then what you end up with, okay, so you get some light that comes out of that, and you, as the name implies, so this is D1, and out here at D2, satisfying the image relation, you end up forming an image. And then what you do is you place your film plane right there. And this is the image. Now you might ask, and then you make a recording there with say an off-axis reference beam like that. So you may ask, so why do you go through all that trouble to do that? Well, it turns out, and we'll derive this later, but the aberrations that you get in reconstructing this hologram depend upon how far and how thick this object is. Okay, so the larger, like if we just did a normal recording where I put a hologram here at some distance d1 away, the aberrations that you would get in the reconstruction depend on that distance d1. In this case, they only depend on the thickness of that object, whatever that was, which could be fairly small. So this particular configuration, which is a transmission hologram configuration, minimizes the reconstruction aberrations, and in particular the chromatic aberration. If you were to re-illuminate this, say, with white light, for normal viewing, you can really restrict those the aberrations and get a decent reconstructed holographic image in transmission. Okay, so there's just one more geometry I want to talk about, but I'll do that next time, and then we'll talk about image analysis of holograms. Okay, so see you on Tuesday. I guess the homework is due then, and have a good weekend. Okay, thanks.